Okay, welcome back. We're going to talk a bit more about this thing called gravitational field now. What do we mean by field? So I want to draw over here the Earth, not to scale. Okay, so there's the Earth. And we want to talk about its influence on objects around it. And as you guys know, and you don't have to write this down obviously, but imagine this is Earth. No matter what we have, whether we have the moon up here, or whether it's a satellite here, or whether it's a person standing on the ground over here, it doesn't matter. Do you agree that the Earth is exerting some kind of invisible influence on all three of those at the same time? It can influence all the objects around it with some invisible effect. And we call that invisible effect a field. It actually creates a field around it that we can't see, but when the objects are in the field, they experience an effect, a force. And I guess the question for physicists is, well, how do we describe the nature of this field? So let me show you how we do this. And it actually is based on the formulas that we've already seen so far. Let's start with our first formula for gravitational field. It is that G is equal to Fg over m. Now, by the way, this is actually a vector equation, weight per unit mass. And the interpretation we get from this one, without going into in great detail, is that Fg, actually, let me go in the other order, sorry. Let's do it this way. I knew that was going to happen. Okay, so let me write that out again. So what this tells us is that G, gravity, has the same direction as Fg on a particular mass. And you got to realize that this mass that we're talking about down on the bottom here, this is a small mass that is placed in the field. It doesn't produce the field, it's a small mass we place into the field. So for example, on my diagram for the Earth here, let's put in a small mass, m, into the field space. Now, when you bring it into that field, and by the way, I'll just put down here on the bottom, here is the Earth with mass big M. So what we're saying is if we want to describe the direction of that field at location M, we start with this. We start with the direction of Fg. And I'm sure you guys are all aware that Fg is going to act towards the center. So if that's actually the case, then that means that gravity must act in the same direction. So G will act in the same direction as the Fg. And you notice that G is acting towards the center of the Earth. And I think we're all comfortable with that gravity acts downward, okay, towards the surface of the Earth. Okay, so that's how we figured out mathematically as physicists, based on that equation. G has the same direction as Fg on a small mass in the field. Okay, good. That's our first thing. But we also have another equation that we derived, and I'm just going to remind you where we came up with it. Do you remember when we wanted to be lazy? Okay, so doing force of gravity for a whole bunch of different objects. And we reduced gm over r squared to that thing called little g, because they were all the same. So there's actually our other equation, gm over r squared. So let's go back and let's introduce that equation. So we have g is equal to g big M over r squared. And what you have to realize in this one is that this m is the large mass, and what we're really talking about is the planetary mass that creates the field. So that's the large mass that actually creates the field. And we have a couple of interesting conclusions that come from this formula here. The first one is, notice that G is proportional to 1 over r squared. So as r increases, as you get further from the planet, G is going to decrease substantially. Okay, so gravity gets weaker the further you go away from the planet. And again, I think we're quite comfortable with that. Another thing is, notice that that formula does not have little m in it. Turns out that gravity is what we call independent of the small mass little m. Here's how I typically teach it to my students. I'll say, okay, well, let's imagine you're in a classroom. What's gravity inside the classroom? And everyone says 9.81. Now, what if everybody left the classroom? What's gravity in the classroom? 9.81. You see, it doesn't depend on whether the little masses are there or not. It's independent of the little mass. It's actually kind of why we like it so much. In physics, we love things that are independent. Same for every situation. See, we like this too, because remember how gravity is 9.81 on the surface? Remember, it doesn't matter what mass it has. Every object falls at 9.81. See, that's awesome. That makes life easier for us to understand. So we love things that are independent, things that we call universal. All right, I won't get into that too much, but now we're going to try to bring in, I'm just going to erase now this part over here. Let's now draw this invisible field that is being created by the Earth. And the way we show it, I'll explain why we do this. We actually show radiating lines like this. So this is an invisible field that it is actually creating. First point is, remember, gravity always has the same direction as Fg. Well, of course, Fg always acts towards the center of the Earth, so no big surprise, gravity will act towards the center of the Earth. So there's the gravitational field acting towards the center of the Earth. Good. And notice that I have not placed any objects in that field space. It exists even when there's no small masses around it. It's independent of the small mass. So we can just draw the field without any masses in it. Now the second detail is I have to show you that as r gets bigger, g gets smaller. And it turns out that's actually being shown in this diagram. Because it turns out, and I'll put this as a side note here, that the strength of g, the strength of the field, is shown by the distance between the field lines. So when the field lines are close together, it's strong. When the field lines are far apart, it's weak. So let me just kind of show you two different locations. If you notice, let's say this location right here. Can you see at this location here, the field lines are actually quite close together. As a result, gravity would be large. This would be gravity at, let's say, this location A. So gravity at A. Because the lines are close together, gravity is bigger. But if we choose a different location, let's see if I have another color I can choose. If I choose a different location out here, you can see that now the lines are very far apart from each other. So we'll call this location B. So therefore this one has a much smaller g. That would be the g at B, because the lines are further apart from each other. So the closer the lines are together, the stronger the field happens to be. So we call this a field diagram. And that describes the gravitational field around a planet. Good? Okay. So let's do a question involving gravity. So what we want to do is find out how far above the surface, as we've really highlighted this phrase, how far above the surface of the Earth would gravity be 5.8 newtons per kilogram? Remember, if you see GFS, gravitational field strength, that's also called little g. I'll put a little bit of a diagram here first to get things started. Here's the Earth. Here's the location above the Earth's surface where gravity happens to be 5.8. So I'm just going to draw that in here. at this location, this gravity is 5.8 newtons per kilogram. And you'll notice that because it's off the surface of the Earth, it is smaller than 9.81. That's good. So that's gravity at that location. And what we're looking for is how far above the surface it is. Well, the first thing we're going to do is we're going to introduce the formula for gravity. We know that G is equal to G, big M, over R squared, where M represents the mass of, in this case, Earth. So we'll put it here, the mass of Earth. And now we can find R. So that's going to be our first goal. We have G R squared is G big ME, and then R squared becomes G big ME over little g. So R, therefore, is going to be the square root of that. Big G, big mass of the Earth, over little g. So again, G is 6.67 times 10 to the negative 11, true anywhere in the universe. The mass of the Earth is actually on the back of your formula sheet. If you look on the back of your formula sheet, it tells you the mass of the Earth. And it'll tell you it is 5.98 times 10 to the 24th kilograms. And for G, careful, it's not 9.81. Remember, in this question, because we're off the surface of the Earth, it's 5.8. So now we can find that value. Square root that. Okay, so I get about 8.2928 times 10 to the 6th meters. But you got to realize what I'm just giving you here, that distance r. Do you remember what the distance r represents? And that is the distance from the center. So from the center to that location, this entire distance, that distance is r. But can you see that that's actually not what we're looking for? We're not looking for the distance from the center. We're looking for the distance above the surface of the Earth. So if I divide that in the diagram, let me just use a different color here. Just trying to figure out what color would be best. We can divide this distance up. See, what I'm looking for is the distance from the surface of the Earth to this location here. So this distance we could call, let's say, d. And you guys realize that the other distance, the rest of the distance, would be the radius of the Earth. So can you see how we would find d? Can you see that all we have to do is subtract the radius of the Earth? And I think I got enough space to do that. So the way I can write that, and I'll just bring this down if you don't mind, just so I don't have to keep on scrolling back up. Put it over here, shrink it down. No, I guess I'm not going to be able to shrink it down. Oh, there I can. Do it that way. Okay, so from here, we could make a formula if you wanted to. We could say that the distance r happens to be equal to the radius of the Earth plus the distance d. So therefore, d would be simply be the distance r minus the radius of the Earth, and that's the key. Subtracting the radius of the Earth. This becomes 8.2928 times 10 to the 6th, and the radius of the Earth is also on the back of your formula sheet. It is 6.37 times 10 to the 6 meters. And we end up getting 1.92 times 10 to the 6th meters. If you're that distance above the surface of the Earth, then you'll have a gravity of 5.8. That means if you dropped an object at that location, it would accelerate downward towards the center of the Earth at 5.8 meters per second squared at that particular moment. Okay, there we go. Now you guys know everything you need to know about gravitational fields. You now can complete the homework. I'll see you in the next lesson.